A perfect pyramid floats against the black of space. This is the enigma of the tetrahedral planet, a world shaped not like a sphere, but like a four-sided die from the cosmos itself. By the end of this journey, you will understand the forces that could forge such a shape and decide for yourself if it points to natural law or divine architects. We will confront a gravity so intense it crushes rock into spheres and explore engineering so advanced it bends entire worlds to its will. What do you believe is waiting for us in the dark? A tetrahedron is geometry's most basic solid, a pyramid with four triangular faces meeting at sharp corners. Now apply that shape to something the size of a world. This is not a slightly squashed sphere like Earth or a flattened disk like Saturn. A tetrahedral planet is a radical departure, a celestial body with distinct flat planes and razor-sharp edges where its gravitational field would be utterly chaotic. To understand why this shape is so shocking, we must first appreciate the universal rule it breaks. Gravity is a sculptor of spheres. It pulls every bit of matter equally toward a center, smoothing out irregularities over time. Think of a water balloon in space. No matter how you deform it, it always snaps back into a sphere because that is the shape where every point on the surface is as close to the center as possible. It is the shape of least energy, of perfect balance. For a rocky world like ours, this pull is so immense that over millions of years, even mountains are pulled down and valleys are filled in, striving for that smooth curve. A stable tetrahedron defies this entire process. It suggests a material or a force so strong, so rigid, that it can resist gravity's relentless embrace. Perhaps its crust is not rock but a single, continent-spanning crystal lattice, unyielding and perfect. Or maybe its rotation is so violently fast that centrifugal force flings material out to those 4 points, creating a spinning top frozen in geometric perfection. The very idea forces us to question everything we assume about how planets form and what they are made of. Gravity's rule makes the search for such a world a hunt for the impossible. So, have our telescopes ever caught a glimpse of a cosmic pyramid? The honest answer is no, not yet. No confirmed tetrahedral planet orbits a distant star in our catalogues. Our planet hunting tools, magnificent instruments like the Kepler Space Telescope and TESS, the Transiting Exoplanet Survey Satellite, work by detecting the faint, periodic dimming of a star's light as a planet passes in front of it. They are built to find spheres or close approximations. A tetrahedral world would create a light curve unlike anything in our models. Instead of a smooth, symmetrical dip, the transit might show a jagged, stepped pattern as the planet's sharp edges and flat planes rotated into view, blocking starlight in a chaotic, geometric dance. It would be a signature of artificiality screaming from the data. This moves the search from pure astronomy into the realm of SETI, the search for extraterrestrial intelligence, and specifically into the concept of Dysonian artifacts. Named for the physicist Freeman Dyson, this idea suggests that an advanced civilization might be detected not by radio signals, but by the colossal structures they build, structures that alter the light of their star in observable ways. A Dyson sphere, for instance, would completely encircle a sun. A tetrahedral planet is a different kind of megastructure, one that reshapes a world itself. Finding one would not be an accident of nature. It would be a deliberate announcement, a monument on a planetary scale. So while we have no confirmed pyramids, astronomers now routinely sift through anomalous data, asking if a strange flicker is a glitch, an unknown natural phenomenon, or the shadow of something built. The search has fundamentally changed. We are no longer just looking for planets, we are looking for artifacts. That search for artifacts leads us to a crossroads. One path points to alien engineering, a conscious design, but the other path, perhaps more unsettling, asks if the universe itself could carve a perfect pyramid. To walk that second path, we must confront the single greatest force standing in its way, the fundamental sculptor of all worlds, gravity itself. Every object in space, from a tiny asteroid to a blazing star, is engaged in a constant, invisible struggle. Its own mass pulls every particle inward toward the center. Over time, this self-gravity smooths and rounds the object into the most stable shape possible, a state scientists call hydrostatic equilibrium. It is the shape of a droplet of water floating on the International Space Station, a perfect sphere, because that shape places every bit of material as close to the collective center of mass as it can possibly be. For a planet, this force is not a gentle suggestion. It is an unimaginable, relentless crush. The rock deep within a planet is not solid in the way we think of it. Under thousands of kilometers of overlying weight, the material becomes plastic. It flows slowly like thick tar, filling in low spots and collapsing high ones. This is why even the tallest mountain on Earth, Mount Everest, is nothing more than a tiny wrinkle on an otherwise stunningly smooth sphere. If you shrunk Earth down to the size of a billiard ball, its surface, including the deepest ocean trenches and the highest peaks, would be smoother than that ball. Now try to impose a tetrahedron onto that billiard ball. You are asking for flat faces and razor-sharp corners to exist where the entire weight of a world is pushing down, seeking that curve. The internal pressures at those sharp edges would be astronomical, likely causing the material to melt, fracture, or flow instantly. To maintain a stable tetrahedron naturally, you would need a planetary crust with the strength of a universe-spanning diamond, something so rigid it could defy the plastic flow that defines planetary interiors. Or you would need a force even more powerful than gravity actively holding that shape together, a mystery that pulls us right back to the edge of something extraordinary. This defiance of gravity demands a world built from something far stranger than rock. To envision a natural tetrahedral planet, we must first dismantle our image of a planetary interior. Forget the molten iron core and churning mantle of Earth. Instead, picture a single, unbroken structure, a lattice that extends from the very heart of the world all the way to its angular surface. The most compelling candidate for such a substance is a form of matter so dense and orderly it behaves like a planet-sized crystal. Imagine a diamond, but not one you could hold. This would be a diamond forged on a cosmic scale, where pressures beyond anything in our solar system force carbon, or perhaps an even more resilient element, into a perfect, rigid alignment. Every atom is locked into place by its neighbors, creating a material of unimaginable strength. In such a world, the crust is not a separate layer. It is merely the outermost face of this monolithic gem. The tectonic plates that shape our planet, the volcanic plumes that erupt from weakness, none of that exists here. The entire globe is one solid piece, immune to the plastic flow that allows spheres to form. It is less a planet and more a celestial geode, cut with geometric perfection by forces we can barely comprehend. But could nature alone create such a thing? The conditions would be extreme. We might be looking at the remnant core of a white dwarf star, a place where matter is squeezed into a degenerate state, electrons pressed so tightly against atomic nuclei that the material becomes phenomenally rigid and dense. Or perhaps it is a world that formed in the insane magnetic fields near a pulsar, where atoms are polarized and assembled into chains of immense strength. These are environments so violent they rewrite the rules of chemistry and physics, places where matter itself is forced into new, stable shapes. A tetrahedron could be one of those shapes, a configuration of minimal energy for a specific, bizarre type of solid. It is a reminder that the universe is a laboratory with recipes we have not yet opened. The crystal planet theory does not just challenge gravity, it challenges our very definition of what a world can be. That crystal world is a monument to stillness, but the cosmos also has a sculptor of motion, a force that pushes outward rather than pulling in. To find a tetrahedron in nature, we might need to set a planet spinning with violent, dizzying speed. This is the realm of centrifugal force. You feel a gentle version of it on a merry-go-round, that sensation of being pushed outward as you spin. On a planetary scale, this outward push fights directly against gravity's inward crush. Our own Earth is not a perfect sphere. Its rotation causes a slight but measurable bulge at the equator, making our planet an oblate spheroid, a sphere gently squashed at the poles. Now imagine cranking that rotation up to an extreme. As a planet spins faster and faster, the equatorial bulge would grow more pronounced. The planet would begin to flatten, stretching outward at its middle like a ball of dough spun between a potter's hands. In theory, if you spun it fast enough, it could distort into a thin disk, a celestial frisbee, but a tetrahedron, that is a far more specific and angular outcome. For a spinning sphere to morph into a four-sided pyramid, the deformation would not be smooth and symmetrical. The material would need to flow and collect not into a continuous rim, but into four distinct lobes or points. This could only happen if the planet's internal structure was not uniform. Perhaps it has a dense, tetrahedral-shaped core that acts as a mold, or its crust has four massive, supercontinent-sized landmasses that act as weights. As the planet spins, centrifugal force would pull these heavy regions outward more forcefully, accentuating their positions at the corners of a tetrahedron, while the areas between them remain pulled inward by gravity. It would be a cosmic balancing act, a temporary and incredibly unstable equilibrium between the push of spin and the pull of mass. The real question is one of limits. How fast can a planet spin before it simply disintegrates? There is a cosmic speed limit called the breakup velocity. Spin a planet beyond that point, and the outward force exceeds its own gravity's ability to hold it together. It would literally fling itself apart, scattering its material into a ring. For a rocky planet like Earth, that critical spin rate is astonishingly fast, a full rotation taking not 24 hours, but roughly 1 hour and 20 minutes. A day would last less than a single movie. At such speeds, the surface would be a nightmare of supersonic winds and tectonic chaos. Maintaining any stable shape, let alone a precise geometric one, seems nearly impossible. The forces involved are so titanic they border on the apocalyptic. Yet, this is where the mystery deepens. Could a planet be born spinning that fast, with just the right internal asymmetry, and then somehow freeze in that deformed state? Perhaps its rapid rotation cools and solidifies its crust in that stretched moment, locking the tetrahedron in place like a snapshot of cosmic turbulence. Or maybe it is not a planet at all, but the remnant of a catastrophic collision, a fragment spun into a strange, stable shape by the violence of its birth. The theory of rapid rotation does not offer easy answers. Instead, it paints a picture of a universe capable of breathtaking violence, where the very axis of a world can become a lathe, shaping matter through sheer, relentless motion. Gravity from a single star sculpts spheres, but gravity from two or more massive objects can become a sculptor of chaos. To find a tetrahedron in nature, we might need to look not at a solitary world, but at a planet caught in a celestial tug-of-war. Picture a world orbiting not one, but two stars in a tight binary system, or perhaps dancing perilously close to a massive gas giant. The gravitational pulls from these multiple bodies do not simply add together. They create shifting, complex fields of force that stretch and squeeze the planet from different directions over and over again. This is the realm of extreme tidal forces. We see a gentle version of this in our own solar system. Jupiter's moon Io is the most volcanically active world we know, not because of internal heat alone, but because the immense gravity of Jupiter, mixed with the pulls from neighboring moons, constantly kneads its interior like dough, generating tremendous friction and heat. Io is tidally locked, always showing the same face to Jupiter, but its shape remains roughly spherical because the forces, while powerful, are relatively consistent. Now amplify that scenario to an almost unimaginable extreme. Imagine a planet in a complex dance with two equally massive stars. Its orbit is not a simple ellipse. It is a chaotic figure-8 path weaving between the two gravitational wells. As it moves, the dominant pull switches from one star to the other. The planet would be stretched toward one star, then suddenly yanked and stretched toward the other. This constant, violent reorientation could, in theory, prevent the planet from ever settling into a relaxed spherical shape. Instead, it might be frozen in a permanent state of deformation. But a tetrahedron that requires a very specific four-lobed kind of stretching. For tidal forces to mold that shape, the orbital dance would have to be perfectly tuned and incredibly unstable. The planet would need to occupy what astronomers call a Lagrange point, a gravitational sweet spot where the pulls from two massive bodies create a zone of equilibrium. But instead of the stable points where objects can park, we would need an unstable one, a point where the planet is perpetually on the edge of falling toward one body or the other, held in a teetering, vibrating balance. The tidal forces at such a point could theoretically pull material into four distinct bulges. Think of it like squeezing a soft ball between four fingers arranged in a pyramid. Each finger is a point of maximum gravitational stress. The real problem is time. Could such a delicate, frenetic orbital configuration last for the billions of years required for a planet to form and cool? It seems astronomically unlikely. The slightest perturbation, the gravitational nudge from a passing star, would send the planet spiraling into one of its suns or hurtling into the dark. A tidally forged tetrahedron would be a cosmic snapshot, a fleeting shape in a universe of spheres, existing for perhaps a mere moment before the music of the spheres went terribly silent. This theory pushes natural forces to their absolute breaking point, asking if chaos itself can, for one brilliant instant, create perfect geometry. All these natural theories push physics to its breaking point. Perhaps the simplest answer is that no natural law carved this pyramid. Perhaps it was built. This brings us to the most profound possibility on the table, that a tetrahedral planet is not a world at all, but an artifact. To understand the scale of such a project, we must look to one of the most famous ideas in theoretical astronomy, the Dyson sphere. Proposed by physicist Freeman Dyson in the 1960s, it is the ultimate expression of a civilization's ambition. Imagine a swarm of satellites or a solid shell completely surrounding a star, capturing every single photon of its light to power a society whose energy needs are beyond our imagination. A Dyson sphere is a signature of a Kardashev Type II civilization, one that has mastered the energy output of its entire star. Now, take that same monumental engineering mindset and apply it not to a star but to a planet. A tetrahedral shape serves no apparent natural function. Its sharp angles and flat planes are inefficient for gravity, problematic for atmosphere, and a nightmare for geology. But for a builder, for an intelligence with a purpose, that geometric perfection is a feature, not a bug. This could be a Kardashev Type II or even Type III project, where a civilization has moved beyond planets and stars to reshape the very structure of galaxies. They are not bound by the need for a habitable surface. They might be converting an entire world into a computational matrix, a cosmic supercomputer where the tetrahedral shape allows for optimal energy flow or data transmission across its crystalline faces. It could be a fortress, its angled planes designed to deflect stellar radiation or weapons fire with perfect efficiency. Or perhaps it is a monument, a piece of galactic art on a scale we can barely perceive, a statement of existence meant to last for eons. The purpose is beyond our comprehension, just as a smartphone would be beyond the comprehension of an ant. The ant might recognize it as a smooth, hard object, but the concepts of circuitry, data, and global communication would be invisible. We are the ants staring at the cosmic smartphone. A Dyson sphere shouts its presence by blotting out a star's light in an unnatural way. A tetrahedral planet does the same, not by its absence of light, but by its impossible presence. It is a shape that should not be, a geometric scream in the silent night. Finding one would be the ultimate proof we are not alone, and that those who came before us operated on a level that turns worlds into clay. But a monument or a fortress still implies a purpose we can vaguely grasp. The true function of an engineered tetrahedron might be something entirely beyond our frame of reference. Think of its geometry not as a shape for living, but as a shape for thinking. This could be a planetary scale computational substrate. Our most advanced quantum computers today require near absolute zero temperatures and precise, stable structures to function. A tetrahedral planet forged from a single crystalline lattice could provide that stability on a cosmic scale. Each atom in that perfect matrix could be a qubit, a unit of quantum information. The entire world becomes a single, unimaginably powerful processor, solving problems that would take our universe's lifetime to calculate. Its sharp edges and flat planes might be necessary for energy distribution or data transmission, channels carved into the fabric of the world itself. Or consider a function more tangible, yet equally staggering. It could be a cosmic lighthouse. A tetrahedron's flat faces are perfect reflectors. If aimed, they could focus the light of its star into a beam of incredible intensity, a signal visible across galactic distances. Unlike a random, spherical world that scatters light in all directions, this geometric shape is a deliberate antenna, a beacon saying, "Here we are," to anyone watching the dark. The terrifying flip side of a beacon is a weapon. Those same focusing faces could concentrate not just light, but other forms of energy, gravitational waves, particle beams, or forces we have no name for into a projectile of stellar magnitude. A single rotation could aim this weapon at any point in its solar system, a silent, omnipotent threat. Yet perhaps the purpose is not destruction but preservation. A tetrahedron maximizes surface area relative to its volume compared to a sphere. For a civilization that has mastered molecular engineering, this entire surface could be a storage medium. Every square inch might hold data or harness solar energy, turning the planet into a library or a battery of galactic heritage. The common thread in all these speculations is utility. A sphere is the shape gravity makes. A tetrahedron is the shape a builder makes when they have a very specific and very powerful job to do. The sheer scale of such a project defies human comprehension. To reshape a world, you would need tools that operate on the same cosmic scale. One terrifyingly elegant possibility is the concept of a von Neumann probe. Imagine a single, self-replicating machine, smaller than a grain of sand, programmed with one directive: disassemble and rebuild. It lands on an asteroid, harvests the raw material, and creates 2 copies of itself. Those 2 make 4, then 8, then a number that quickly becomes astronomical. This exponential swarm, named for the mathematician John von Neumann, would spread like a cosmic tide. A single probe sent to a target planet could, within a geological blink, become a trillion machines, a gray goo of purpose. They would not just cover the surface, they would burrow into the mantle and core, atom by atom, deconstructing the entire spherical world into a cloud of raw elements. Then, guided by a blueprint older than our sun, they would begin the reassembly. Picture a planet-sized 3D printer using the very substance of the world as its ink. The swarm would deposit material not into the relaxed shape of a sphere, but onto the rigid scaffolding of a tetrahedron, building up the flat faces and sharp edges according to a plan written in pure geometry. The old planet is gone, consumed to create the new. This method does not fight gravity, it simply removes the planet from existence and puts something else in its place. It is the ultimate recycling project, executed by a silent, patient swarm that sees a world not as a home, but as raw material. But what if you wanted to reshape a living world, to mold it like clay without destroying it? That requires a mastery over the fundamental force that holds the universe together, gravity itself. For us, gravity is a constant and invisible chain that pins us to the ground. For a civilization capable of engineering planets, it might be just another tool in the workshop. The theoretical concept of a gravity generator or a gravity lens moves from science fiction into the realm of staggering possibility. Imagine placing massive devices in precise orbits around the planet, devices that can project and manipulate gravitational fields with pinpoint accuracy. To flatten a face of the tetrahedron, you would not need to physically push the rock. Instead, you would increase the apparent gravity pulling on that entire region, coaxing the molten, plastic material of the mantle to flow and settle into that flat plane. To sharpen a corner, you would lessen gravity's pull there, allowing material to rise and solidify into a peak. It would be a slow, meticulous process, like a potter using not just their hands, but an array of invisible forces to shape the spinning clay. The planet remains whole, its biosphere perhaps even preserved under vast temporary shields, as its very foundation is gently, irresistibly persuaded into a new form. This is engineering not of matter but of space-time, a demonstration of power so complete it edits the laws of physics to suit its design. The most extreme method, however, makes even gravity manipulation seem quaint. It is the direct conversion of mass into energy and back again, the ultimate alchemy promised by Einstein's famous equation. In this scenario, the builders do not move the planet's material, they transform it. Enormous orbital facilities, perhaps powered by miniature stars or the energy of a Dyson sphere, would direct beams of pure energy at the planetary body. These beams would not simply heat or cut, they would unravel matter itself at the subatomic level, converting a section of the crust into a temporary, controlled energy state. That energy, held in a precise force field, is then reconstituted as matter, but in a new configuration with new atomic bonds, creating a substance of impossible strength and purity. The tetrahedron is not built from rock, but from this engineered material, grown layer by layer like a crystal in a lab, while the original planet is slowly digested and converted into the building blocks of the new. This is creation ex nihilo on a planetary scale, turning a lump of cosmic dirt into a geometric masterpiece of flawless synthetic matter. The finished product might share no more with its original self than a polished diamond shares with a lump of coal. It is a total transcendence of the natural order, a final, definitive statement that for its builders, the universe is not a set of constraints but a palette. The universe is a master of repetition. Across billions of galaxies, gravity carves the same spheres, nuclear fusion ignites the same stars, and cosmic dust coalesces into the same familiar world. This very consistency is what makes the search for the extraordinary so meaningful. When we scan the heavens and find nothing but round worlds, it is not a failure. It is a confirmation of the rules as we understand them. The profound absence of naturally occurring tetrahedral planets in our data might be the most compelling clue of all. If our most extreme models of crystal cores, violent spins, and chaotic orbits all point to the same conclusion, that such a shape is astronomically unstable or fleeting, then the appearance of one, stable and enduring, would scream of something else entirely. It would become a premier candidate for a technosignature, an artifact of intelligence written across light years. This moves the conversation from speculative astronomy into the heart of one of humanity's oldest and most haunting questions, the Fermi paradox. Physicist Enrico Fermi famously asked, if the universe is so vast and old, where is everybody? The silence has been deafening. We have listened for radio signals and found none. We have searched for Dyson spheres and found none. The great cosmic zoo appears empty. A tetrahedral planet would shatter that silence in an instant. It would not be a whisper or a signal that could fade. It would be a monument. It would be an answer not to the question of where they are, but to what they are capable of. They are out there, and they do not just inhabit worlds, they reshape them. They take the fundamental clay of creation and sculpt it into forms that defy the very laws that govern our own existence. The discovery would resolve the paradox with staggering finality. The reason we have not heard their broadcasts is not because they are hiding or extinct. It is because their language is not made of radio waves. It is written in the geometry of planets. Their communication is not a message sent, but an artifact left, a permanent signature etched into the fabric of a solar system, waiting for a species with telescopes and curiosity to finally look up and understand. The scale of such a project answers another, darker part of the paradox. Perhaps civilizations do not last long, perhaps they self-destruct. But a structure built to endure for billions of years suggests a mindset that thinks in epochs, not elections. It implies a stability and a purpose that transcends any crisis we can conceive. Finding a cosmic pyramid would not just tell us that aliens exist. It would tell us they are builders, thinkers, and artists of cosmic magnitude. It would tell us the universe is not just a wilderness of stars, but a gallery. And somewhere in the dark, a masterpiece is waiting. A monument of that scale forces us to ask where science ends and speculation begins. The line is surprisingly thin. Within the rigorous halls of theoretical astrophysics, scientists have already mapped the boundaries of possible worlds, and some of those maps include shapes that defy the sphere. While a stable tetrahedron remains beyond the edge of the chart, the very act of drawing these maps proves a crucial point. The cosmos can be far stranger than our everyday experience allows. This is not science fiction musing. This is the work of researchers using the hard language of mathematics and physics to ask, what are the absolute limits of a planet's form? One of the most fascinating thought experiments to emerge from this line of inquiry is the toroidal planet, a world shaped like a donut. Astronomer Mark J. Kuchner, working at NASA, a Goddard Space Flight Center, has published papers seriously exploring the conditions under which such a planet could exist. The concept is a masterpiece of cosmic balance. Imagine a planet spinning so incredibly fast that centrifugal force doesn't just create an equatorial bulge, it punches a hole straight through the middle. The material is flung outward with such violence that it stretches into a ring, with the planet's stars shining through the central hole. For this to be stable, the rotation would have to be precise and the planet's composition just right, likely a fluid or gaseous world rather than solid rock. Gravity would pull inward everywhere while spin pushes outward, creating a delicate, dynamic equilibrium. The toroid or ring shape becomes a mathematically valid, if extremely unlikely, solution to the equations of planetary formation under extreme duress. This work does more than just imagine a bizarre world. It stretches our understanding of hydrostatic equilibrium, the very rule that demands spheres. It proves that under a specific, narrow set of violent conditions, gravity can be forced to settle into a shape that is not a sphere but a ring. It is a natural stepping stone from the familiar to the alien. If a donut-shaped planet can exist in theory, even if we never find one, then the door is cracked open for other non-spherical forms. The tetrahedron is a far more angular and specific challenge, but the principle is the same. By rigorously exploring the toroid, scientists like Kuchner are not just playing with ideas. They are stress-testing the laws of physics. They are asking how far you can push a system before it breaks or, more intriguingly, before it transforms into something entirely new. This academic work provides a vital bridge. It takes the concept of exotic planets out of the realm of pure fantasy and plants it firmly within the landscape of legitimate scientific inquiry. When we look at a cosmic pyramid, we are not just seeing a wild guess. We are seeing an extreme extension of a conversation that has already begun in the pages of peer-reviewed journals. The universe's workshop may have more blueprints than we ever dared to file. This rigorous scientific groundwork for strange worlds brings us to a crucial point in our search, the moment we look at the data and see something that should not be there. For decades, astronomers have catalogued anomalies, signals, and flickers from the dark that defy easy explanation. These are not potential tetrahedral planets, but they are the kind of cosmic static that forces us to ask new questions. Could some of these famous, unsolved mysteries be reinterpreted through the lens of a tumbling, geometric world? Let us revisit two of the most tantalizing enigmas in the sky, starting with a signal that lasted just 72 seconds but has echoed for decades. In August of 1977, the Big Ear radio telescope at Ohio State University was sweeping the sky, listening for the faint whispers of cosmic radio waves. Most of the data was noise, the static hiss of the universe. But on one printout, astronomer Jerry Amon saw a sequence of letters and numbers so startling he circled it and wrote a single, powerful word in the margin: "Wow." The signal was 30 times stronger than the background noise, and it matched the exact frequency that scientists predicted an intelligent civilization might use to broadcast its existence, the hydrogen line. It came from the direction of the constellation Sagittarius, lasted for 72 seconds, and then vanished, never to be heard again. For 45 years, the WOW signal has resisted all natural explanations, from comets to passing satellites. It remains the strongest candidate for a deliberate signal from beyond our solar system. Now, let us shift our perspective. What if it was not a message but a byproduct? Imagine a tetrahedral megastructure, a colossal geometric shape tumbling slowly end over end in the void. Its flat, metallic faces could act as perfect mirrors for certain radio frequencies. If one of those faces happened to align perfectly with Earth at just the right angle, for just the right moment, it could reflect the natural radio chatter of its own star or a nearby cosmic event directly at us. The reflection would be fleeting, a brilliant flash in the radio spectrum that disappears as the face rotates away. It would be a cosmic glint, like sunlight flashing off a distant satellite, but on a scale that drowns out the background noise of the galaxy. The WOW signal was not a repeating pattern or a coded message. It was a burst, a single, powerful ping that fits the profile of a reflection from a rotating, irregular object far better than it fits a steady, intentional beacon. The mystery deepens when we turn from radio waves to the dance of light. In 2015, citizen scientists poring over data from the Kepler telescope flagged a star that did not make sense. KIC 8462852, nicknamed Tabby's star after astronomer Tabitha Boyajian, was dimming in ways no natural model could fully explain. The star's light would dip by enormous amounts, up to 22%, in irregular, jagged patterns. It was not the smooth curve of a spherical planet. It looked chaotic, as if a swarm of objects of all different shapes and sizes were passing in front of it. The leading natural theory involved a vast cloud of dusty comet fragments. But the sheer scale and irregularity of the dimming left room for wilder speculation, including the idea of a partially built alien megastructure, a Dyson swarm under construction. Now inject our tetrahedral planet into that scenario. Picture a geometric world, not in a clean orbit but tumbling erratically, perhaps after some cataclysmic event or as part of its intended function. As it transits its star, its 4 triangular faces and 3 sharp edges would block the light in a sequence of steps and jagged dips. The light curve would not be a single, clean U-shape. It would be a staircase, a series of sudden drops and plateaus as each flat plane and each corner moved across the stellar disk. Furthermore, if the object was tumbling, no two transits would look the same. One pass might show a deep, prolonged dip from a broad face. The next might show a series of quick, sharp spikes as the vertices grazed the star's light. This creates exactly the kind of erratic, aperiodic, and deeply puzzling signature that Tabby's star displayed. It is a playful, speculative thought experiment, not a solution. But it serves a vital purpose. It forces our imagination to work in reverse. We are not starting with a theory and looking for proof. We are starting with an undeniable anomaly, a splotch on the data, and asking what kind of physical object, however improbable, could possibly create it. The WOW signal and Tabby star remind us that the universe is still full of raw, unexplained data. Our job is not to force these mysteries into known boxes, but to let them stretch the boxes until new shapes emerge. Sometimes the answer is a cloud of dust. Sometimes it might be the tumbling shadow of a cosmic pyramid. Finding a tetrahedral planet would be the beginning, not the end of the mystery. Our first task would be to understand its bones, to listen to its heartbeat. This is where planetary geology and seismology become our stethoscopes for a world that defies all medical textbooks. On a spherical planet like Earth, seismic waves from an earthquake ripple outward in expanding spheres, bending and slowing as they pass through different layers of crust, mantle, and core. They tell a story of a concentric, layered interior, but on a tetrahedron, that story would be written in a language of harsh geometry. Seismic waves generated at one of its flat faces would not spread in gentle curves. They would travel in unnervingly straight lines along that immense, rigid plane, like a sound echoing down an infinitely long hallway. When they reached one of the world's sharp edges, they wouldn't gradually refract. They would reflect with a violent, crisp ping, bouncing off the geometric boundary as if hitting a mirror. The entire planet would ring like a bizarre, four-sided bell. The seismic signature we would detect from orbit or from surface probes would be a jagged, angular pattern of echoes, a stark map of flat planes and perfect corners. There would be no gentle transition zones, no evidence of a molten outer core sloshing beneath a brittle crust. The data would suggest a single, monolithic solid, perhaps with a complex internal lattice, but utterly devoid of the plastic, flowing layers that define a living world like our own. This seismic fingerprint would be our first hard proof that we were not standing on a planet shaped by gravity, but on a structure engineered for stability. Its geology would be a flat, silent plain stretching to a geometric horizon, with no mountain ranges born of clashing tectonic plates, no river valleys carved by erosion, and no volcanic chains marking hotspots in a churning mantle. The very ground beneath our feet would be a finished surface, a tabletop on a cosmic scale. This leads to another profound mystery, the question of a magnetic field. Earth's protective magnetic shield is generated by the churning of molten iron in its outer core, a dynamo powered by our planet's rotation and internal heat. A tetrahedral world, if it is a solid crystal, would have no liquid metal core to churn. It might possess no global magnetic field at all, leaving its surface exposed to the full fury of stellar radiation and cosmic rays. Or its field could be something entirely alien. If the tetrahedron is an active machine, its magnetic field might be artificially generated, projected from massive installations at its vertices or induced across its crystalline lattice. Instead of a dipole field shaped like a giant bar magnet, it could be a tetrahedral field itself, with lines of magnetic force concentrated and focused along its edges, creating zones of intense magnetic activity at its corners. These sharp points protruding into space would act not as rounded hills but as lightning rods for the cosmos. Solar wind, that constant stream of charged particles from its star, would be funneled and accelerated along those magnetic channels, potentially creating permanent, dazzling auroras that crown each of the four vertices in a silent, geometric storm. The corners might glow with an unearthly light, not from reflected sunlight, but from captured stellar fury, marking the points where the architecture of the world interacts most violently with the sea of space around it. To study such a place would be to realize that every tool in our scientific kit, designed for understanding spheres, would need to be reinvented. We would be geologists mapping a sculpture, seismologists listening to a crystal bell, and physicists decoding a machine whose primary purpose remains hidden in plain sight, written in the angles of its impossible silhouette. That silent, geometric surface would rewrite the rules of the sky itself. An atmosphere on a tetrahedral planet is not a simple blanket of air. It is a fluid trapped on a shape with no curves, forced to navigate a landscape of infinite plains and impossible cliffs. Picture standing on one of those vast, flat faces. The horizon would not be a gentle curve dipping away. It would be a razor-straight line meeting the black of space, a geometric cliff edge where the ground simply ends. The air above you would behave in ways that defy every weather pattern we know. On Earth, our atmosphere flows over a spherical surface curving with the planet. Here, it would slam into a wall. Prevailing winds, driven by the planet's rotation and temperature differences, would travel unimpeded across the flat plane until they reached the edge. With no gradual slope to rise over, the air mass would be forced upward in a sudden, violent updraft. This perpetual collision at the perimeter of every face would create a permanent ring of superstorms, a continuous hurricane of unimaginable power raging where the sky meets the geometry of the world. The cloud formations would be equally alien. Instead of the puffy cumulus or layered stratus we see, you might witness vast hexagonal cloud sheets, their patterns locked into the standing waves of air vibrating across the flat plane. Over the interior of the face, the weather could be eerily calm, even stagnant, while the edges roar with eternal tempests. The true chaos, however, would be reserved for the vertices, the three sharp corners where the edges meet. These are not rounded mountain peaks. They are singular points in space where three flat planes and three razor edges converge. Think of them as the planet's atmospheric drains. Wind rushing along the edges from different faces would collide at these points, creating a permanent, hyper-intense vortex. It would be a tornado that never dies, a maelstrom of air spinning with such ferocity it might tear the atmosphere itself into layers. The low pressure at the tip of a vertex could suck air down from the upper atmosphere, creating a permanent fountain of descending wind that then radiates back out along the edges. These vertices would not just be points on a map. They would be dynamic, screaming engines of weather, visible from space as swirling caps of furious cloud. Lightning on such a world would be less a random strike and more a predictable geometric display. The intense friction from air masses shearing along the edges and colliding at vertices would generate staggering amounts of static electricity. Lightning might not flash from cloud to ground in jagged bolts. Instead, it could manifest as continuous, luminous sheets dancing along the entire length of an edge, a permanent electric border tracing the world's geometry. Or the vertices could act as cosmic lightning rods, each one crowned by a perpetual, silent storm of purple and blue discharges, a beacon of raw energy marking the corners of creation. To visualize this, scientists can run dynamic weather simulations on a tetrahedral model. The results are both beautiful and terrifying. The fluid dynamics of the atmosphere render the invisible shape of the world in cloud and storm. The flat faces appear as calm, clear zones, while the edges glow with dense, turbulent bands of cloud. At each vertex, the simulation shows a tight, brilliant spiral, a pinwheel of permanent hurricane. It looks less like a planet and more like a carefully engineered climate system, where weather is not a process but a consequence of architecture. This is a sky without compromise, where the atmosphere is forced to obey the harsh, angular law of the ground below. It is a place where you could forecast the weather for 1,000,000 years with perfect accuracy, because the storms are not born of chaos, but are forever locked into the immutable angles of a world that was built. The sky above is not a dome, but a geometric puzzle. You stand on a plane of dark, seamless stone that stretches toward a horizon line so sharp and straight it feels unnatural. This is not the gentle curve of Earth. It is the abrupt mountain ridge edge of the world itself, a cliff that drops into an infinite gulf of stars. As you turn, your gaze follows a colossal seam rising from that edge, a line where two other faces of the tetrahedron meet, angling up into the heavens like the sides of a mountain built by gods. The sun here does not rise or set in an arc. It slides along the inside of that angular valley where the faces meet, its light crawling across the plane in long, stark shadows until it vanishes abruptly behind the razor edge, plunging your entire face into instant night. A day might last for standard hours, but the transition is not a twilight glow. It is a shutter closing. The stars that emerge do not wheel in circular paths. They travel in straight lines, parading in military precision along the geometric channels of the sky, their trajectories bending only when they pass behind the stark silhouette of a vertex piercing the heavens. If this world has moons, they would not wax and wane in a cycle. They would appear as jagged, moving shapes, their light blinking erratically as they pass behind the world's own sharp edges, casting strange, angular shadows that race across the ground. Your very weight might change as you walk. Gravity on a tetrahedron is not uniform. On a sphere, gravity pulls you straight down toward the center. Here, on a flat face, the pull is still mostly downward, but as you approach that sheer edge, the mathematics of attraction becomes strange. The mass of the adjacent face pulls at you diagonally. You might feel a slight but perceptible tug toward the world's edge, a sensation of being drawn toward the abyss not by vertigo, but by the literal pull of the planet's own shape. Walking toward the horizon, your steps could grow heavier or strangely lighter, as the combined gravity of multiple faces interacts in a way no human body has ever felt. The silence would be absolute, broken only by the wind howling along the seamless stone, destined for that eternal storm at the edge. This is a landscape built by calculation, where every line of sight ends in a perfect, terrifying angle. To stand here is to understand that you are not on a world. You are on a structure, and you are walking across one of its faces, a tiny figure on a drawing of cosmic geometry. This harsh geometry forces a profound question about the nature of life itself. Could anything live on a tetrahedral world? If it is a natural formation, the environment seems almost designed to snuff out biology. Life as we know it thrives on gradients and cycles, on the gentle mixing of atmosphere and ocean across a spherical surface. Here, the very factors that might create the shape would also create a sterile nightmare. The potentially uneven gravity, strongest at the faces and strangest at the edges, would make fluid circulation a chaotic mess. Plants and animals evolved for a consistent downward pull would find their internal systems confused, their growth patterns warped. The focused radiation and eternal storms at the vertices would create zones of utter devastation, lethal barriers that could isolate any potential ecosystems on different faces entirely. There would be no global water cycle, no way for nutrients to spread from one face to another across the void of a geometric cliff. Each flat plane would be an isolated island in the sky, a captive ecosystem with no connection to its neighbors. The sheer silence of the geology, the absence of tectonic renewal and volcanic outgassing, suggests a world that is geologically dead, with no internal engine to replenish atmospheres or recycle chemicals. For natural life to arise here, it would have to be a form of biology we cannot yet conceive, perhaps one that draws energy directly from the crystalline lattice of the planet itself, or feeds on the electrical storms along its edges. It is a bleak, lonely picture, but if this world is an artifact, the question of life transforms completely. The builders would not have shaped a cosmic pyramid to live on its harsh, natural surface. They would have built the surface itself. Each vast, flat face could be a perfectly engineered plate, a continent-sized habitat enclosed under a transparent, kilometer-high dome. Inside, gravity is not a variable force of nature, but a controlled parameter, dialed to a comfortable, Earth-like standard across the entire plane. The furious storms at the edges are not a threat, but a power source, their energy harvested by the colossal structures at the vertices to fuel the endless day within. The sun that slides along the angular valley is not a distant star, but a series of artificial suns traversing a ceiling, simulating perfect seasons in a controlled cycle. This is not a world that evolved life, it is a world that curates it. The tetrahedron becomes the ultimate ark, a biological preserve of staggering scale. Each face could house an entirely different ecosystem, a snapshot of a world long gone or a masterpiece of synthetic biology, all maintained in perfect, timeless stasis. The sharp edges and vertices are not flaws, but the structural supports for this immense terrarium, the exoskeleton that allows the interior to be a paradise. Perhaps the builders still inhabit it, living in cities that look like geometric art, their culture shaped by the perpetual straight-line horizons. Or perhaps they are long gone, and the tetrahedron is a silent zoo, a museum of galactic biodiversity waiting for a new caretaker. The life inside would not struggle against the environment. It is the environment, every blade of grass and every flowing stream placed according to a design older than our sun. In this light, the tetrahedron is the most profound act of care imaginable, a fortress built not for war, but for preservation, ensuring that life, in all its forms, endures long after the stars that birthed it have cooled. The choice is stark, a sterile accident of physics or the greatest sanctuary ever built. The answer lies in the details, in the silent signals it might still be sending. The silent sanctuary of a tetrahedral world points to a search that has been looking in the wrong direction. For decades, the quest to find other civilizations has been defined by a single, powerful assumption that intelligence announces itself with a signal. We have aimed our radio telescopes at the stars, listening for a structured message, a deliberate hello. We have trained our space telescopes on distant atmospheres, hunting for the chemical fingerprints of life, the oxygen and methane of a living biosphere. These are biosignatures, the evidence of biology, and they are profound, but they are also whispers in a cosmic wind, fragile and fleeting. A tetrahedral planet is not a whisper. It is a scream carved in stone and set against the void. It represents something entirely different, a technosignature. This is the evidence not of life, but of technology and engineering on a scale that dwarfs planets. It is a permanent, physical monument that declares its builder's existence not through a transient radio burst, but through the immutable defiance of natural law. Finding one would not just add a new data point to SETI, it would shatter the paradigm. The search would irrevocably shift from eavesdropping on conversations to archaeology. We would no longer be listening for a voice. We would be studying the ruins or perhaps the active machinery of a civilization that thinks in continents and sculpts with gravity. The tools of the hunt would change overnight. Astronomers would pore over old telescope data, not for anomalous radio spikes, but for anomalous light curves, for stars with transits that look like staircases or shadows with too many sharp angles. Planetary scientists would model not habitable zones, but the stability of impossible shapes. The great question would become not are they speaking, but what did they build and why does it look like that? A technosignature is a message that does not fade when the transmitter powers down. It is a signature written across light years with the mass of a world, waiting to be read by anyone who learns to see the universe not just as a collection of natural objects, but as a potential gallery of artifacts. This transforms the Fermi paradox from a question of communication into a question of perception. The silence we hear may not be an empty silence. It may be the quiet of a museum where the exhibits are so vast we have mistaken them for the walls. The discovery of such a monument would force a reckoning far beyond science. We would be faced not just with a new object in space, but with a new chapter in the story of existence, one where our own chapter suddenly seems like the opening sentence. This is the deepest philosophical tremor a tetrahedral planet would send through our civilization. A challenge to our cosmic significance so profound it would echo for generations. For all of human history, we have measured our progress against the natural world. We have built pyramids, cities, and now digital networks that span the globe, seeing ourselves as the pinnacle of ingenuity. But to find a world reshaped into a perfect geometric form, is to be shown our own efforts as the scribbles of a child in the margins of a master's blueprint. It is the ultimate act of cosmic humility. We are not the first, and we are certainly not the greatest. Our understanding of physics, which we treat as the immutable laws of the universe, would be revealed as merely the local bylaws. The builders of such a world did not just obey physics, they edited it. They treated gravity not as a chain, but as a tool. They treated matter not as a given, but as a raw material to be transmuted. Our most advanced theories about warp drives and quantum engineering would be relegated to the status of ancient alchemy, the fumbling first steps of a species just learning that the universe has a user manual we have not yet found. The very timeline of intelligence would be shattered. Our civilization is a mere few thousand years old from its first cities to its silicon chips. A stable tetrahedron, built to last for billions of years, implies a civilization that has endured for epochs, that thinks in units of time where mountain ranges rise and fall. It asks a terrifying question: are we looking at our own distant future, a glimpse of what humanity might become if we survive our own adolescence? Or are we looking at the relics of beings so ancient they were sculpting worlds when our solar system was still a cloud of dust, gods who have since moved on or vanished, leaving their monuments behind as cosmic tombstones? This distinction cuts to the heart of our search for meaning. If they are our future, it offers a fragile thread of hope, a proof that intelligence can navigate the perils of technology and achieve a stable, enduring grandeur. But if they are ancient ghosts, it suggests a darker possibility, that even the mightiest civilizations eventually fade, leaving only their silent, geometric bones adrift in the dark. In either case, our place is redefined. We are no longer the protagonists of the cosmic story. We are late arrivals in a theater where the stage itself was built by hands we will never see, walking onto a set whose true purpose we can only guess. The universe becomes less a wilderness to conquer and more a library to study, filled with books written in the language of gravity and geometry, waiting for us to learn how to read. The hunt for a cosmic pyramid begins not with grand theories, but with patient, meticulous observation. Our first and most powerful tool is the analysis of starlight. When a planet passes in front of its star, it blocks a tiny fraction of that light. For a spherical world, this creates a smooth, symmetrical dip in the star's brightness, a predictable U-shaped curve in the data. A tetrahedral world would tell a different story. Its transit would be a geometric signature. As its first sharp vertex began to cross the star, the light would drop in a sudden, discrete step. Then, as a flat face moved fully into view, the dimming would plateau, holding steady. Another step would occur as that face's edge passed, followed by another plateau. The resulting light curve would look like a jagged staircase, a series of abrupt drops and flat lines completely unlike the gentle curve of any natural sphere. Astronomers already have algorithms scanning for anomalous transits. They are now being refined to flag these unnatural, angular patterns, turning a telescope's photometer into a detective scanning for shadows with too many corners. Beyond the shape of the shadow, we can search for the heat signature of something that should not exist. Every object gives off infrared radiation, a glow of heat. A natural planet radiates this heat relatively evenly from its sun-warmed surface. An artificial megastructure, however, might have a radically different thermal profile. The vast, flat faces of a tetrahedron could be perfect radiators, shedding heat efficiently into space and appearing cooler than expected. Conversely, the vertices or edges might house immense power systems, glowing with intense, localized infrared heat that stands out like a beacon against the cold backdrop. Telescopes like NASA's Wide-Field Infrared Survey Explorer, or WISE, have already mapped the sky in infrared, creating catalogs of warm objects. Sifting through this data for point sources with bizarre, non-stellar heat distributions is another way to hunt for the engine rooms of a geometric world. The next leap in our search will come from the next generation of observatories, instruments that can dissect light with unimaginable precision. The James Webb Space Telescope is not just a camera, it is a cosmic chemist's lab. When starlight filters through a planet's atmosphere, specific molecules absorb unique colors, leaving fingerprints in the spectrum. Webb can read these fingerprints. For a candidate tetrahedral world, the atmospheric spectrum would be the ultimate test. A natural terrestrial planet might show signs of water vapor, carbon dioxide, perhaps even oxygen from biology. The atmosphere of an artifact could be utterly alien. It might show no molecules at all, suggesting a perfect vacuum maintained under a shield. Or it might reveal exotic, industrial compounds not found in nature, or isotopes in ratios that scream of artificial enrichment. It could even show evidence of a perfectly uniform, engineered atmosphere across the entire face, something impossible on a dynamic, weather-ridden sphere. Webb gives us the ability to sniff the air of distant worlds, and the smell of machine oil or perfect sterility would be as shocking as the shape itself. This monumental task is not for professional astronomers alone. The dataset of the cosmos is now so vast that it exceeds the capacity of any single team to analyze. This is where you can join the hunt. Citizen science platforms like Zooniverse host projects where anyone with an internet connection can help examine real astronomical data. You might be asked to classify light curves from the TESS satellite, looking for the telltale stair-step pattern among thousands of smooth dips. Or you might scan infrared images, flagging unusual point sources for further study. Projects like Planet Hunters have already led to the discovery of exotic planets by dedicated volunteers. The next great anomaly, the shadow that doesn't fit, could be spotted by a teacher, a student, or an enthusiast sitting at their kitchen table. The search for a tetrahedral planet is more than a scientific endeavor. It is a collective act of curiosity, a way for humanity to train its many eyes on the dark and ask together, what else is out there? The stark, angular shadow of a tetrahedral world is not confined to scientific journals. It has already taken root in our collective imagination, thriving in the fertile soil of science fiction. Long before astronomers ran their first simulations, storytellers were dreaming of geometric planets. In Larry Niven, Jerry Pournelle, and Stephen Barnes's novel The Legacy of Heorot, explorers encounter a world with a startlingly angular moon, a hint of cosmic architecture that shapes their entire struggle. Video games have built entire ecosystems on such concepts, crafting levels and lore around worlds with impossible geography. These fictional depictions are more than just entertainment. They are a vital part of the discovery process, a creative synergy that stretches the boundaries of what we believe is possible. Science fiction acts as a cosmic sandbox. Unburdened by today's budgetary limits or technological hurdles, writers and artists can ask the wildest what-if questions. What if a planet didn't rotate? What if its crust was a single crystal? What if ancient beings built a monument the size of a world? By visualizing these ideas, by giving them shape in a movie scene or a game environment, they plant a seed in the minds of the next generation of scientists and engineers. The iconic spinning space station in 2001, A Space Odyssey, didn't just look cool. It made the concept of artificial gravity through rotation tangible and plausible for millions. The artistic renderings of Dyson spheres and ring worlds that fill online galleries are not just pretty pictures. They are visual hypotheses, forcing us to confront the scale and the staggering implications of such constructs. When we see a beautifully rendered piece of concept art showing a tetrahedral planet hanging in a nebula, its faces catching the light of a distant sun, we are not just admiring art. We are conducting a thought experiment in visual form. That image asks us to consider the atmospheric patterns, the strange day-night cycles, the sheer engineering audacity. It makes the abstract concrete, and in doing so, it inspires real scientific curiosity. someone might see that image and be driven to calculate the gravitational stresses at the vertices. Another might model the climate on one of those vast plains. The line between speculative fiction and scientific inquiry is beautifully porous. The scientists who rigorously modeled toroidal planets today likely grew up reading the very stories that first imagined them. This cultural conversation, this back and forth between the rigor of the lab and the boundless creativity of the human mind, is how we prepare ourselves for the truly unexpected. By celebrating these fictional visions, we are not abandoning science. We are expanding its vocabulary, training our minds to recognize the silhouette of the impossible against the starfield of the known. But for every breathtaking vision of cosmic architects, a grounded voice of skepticism demands to be heard. This voice speaks not of possibilities, but of probabilities, armed with the most reliable tool in science, the relentless laws of physics. The argument is simple and powerful. Gravity works. We have observed its handiwork across the universe, from the smallest asteroids that eventually pull themselves into round shapes to the largest gas giants. The spherical form is not a suggestion. It is an inevitable outcome for any object above a certain size given enough time. Every single confirmed exoplanet in our catalogues, every world we have ever directly or indirectly observed adheres to this rule. To propose a stable tetrahedron is to propose an exception to a universal law supported by countless examples, without a single verified counterexample. This is an extraordinary claim, and as the saying goes, extraordinary claims require extraordinary evidence. So far, we have none. We have fascinating anomalies like Tabby's star, but those have found plausible, if complex, natural explanations involving vast clouds of dust. We have theoretical models that push boundaries, but they show such shapes are fantastically unstable. The skeptic asks a piercing question, which is more likely that we have discovered a completely new, physics-defying state of matter and planetary formation, or that we are misinterpreting a strange but natural phenomenon. This is where Occam's razor, a principle of problem-solving, cuts to the heart of the mystery. When faced with competing explanations, the one that requires the fewest new assumptions is usually correct. The natural explanation for a strange light curve might be a swarm of comets, an oddly tilted ring system, or a planet with a highly irregular but still roughly spherical shape shrouded in violent dust storms. These are complex, but they operate within known physics. The alien megastructure explanation, by contrast, requires a cascade of new assumptions, a hyper-advanced civilization, technology beyond our comprehension, a motive for building, and a cosmic timescale for construction. The simpler path points to a weird natural world, not a silent monument. Our own psychology also plays a trick on us in this search, a powerful bias called pareidolia. This is the innate human tendency to see familiar patterns in random data. We see a face in the clouds, a rabbit in the moon, or the silhouette of a pyramid in a mountain on Mars. Our brains are wired for pattern recognition, a survival trait that helped our ancestors spot predators in the brush. But in the vast, noisy dataset of the cosmos, this same trait can lead us astray. A few anomalous data points in a light curve can feel like a signal, a geometric pattern emerging from the chaos. We might be desperate for a sign, for contact, and so we project our hopes onto the static. The skeptic reminds us to temper wonder with rigor, to ensure our longing for cosmic company does not paint faces onto the random stones of the universe. This balanced view does not diminish the mystery, it deepens it. It forces the question to become more precise, more powerful. If it is not aliens, then what natural phenomenon could possibly mimic such a perfect geometric signature? The answer pushes our understanding of planetary science to its absolute limits, into realms of physics we are only beginning to map. The true enigma lies in the tension between what our imagination can conceive and what the cold, hard laws of the universe actually permit. The ultimate resolution of this cosmic geometry puzzle lies not in our current telescopes, but in the ones we are building. Our vision is about to expand in ways that will make today's planet hunting feel like squinting through a fogged window. The next generation of ground-based giants, like the 30-meter telescope, will gather more light than every telescope built before it combined. With a mirror spanning the length of a blue whale, it will peer into the atmospheres of distant worlds with stunning clarity, potentially detecting the unnatural chemical signatures or the bizarrely uniform weather patterns of a geometric world. But to truly see the shape of an exoplanet, we must go beyond our atmosphere's blurring effect. The future belongs to space-based interferometers, a concept of breathtaking ambition. Imagine not one telescope, but a fleet of them, flying in precise formation thousands of kilometers apart in the silent void. By combining their data, they act as a single, virtual telescope with a lens as wide as the distance between them. This synthetic eye could achieve a resolution so sharp it might one day not just detect a world, but actually map its silhouette. We could watch as a pixelated dot resolves into a distinct shape. Would it be a fuzzy sphere, or would we see the stark, straight lines and sharp corners of a cosmic pyramid? The data would no longer be a suggestive light curve or a strange spectrum. It would be a photograph. The image might be grainy, a handful of pixels across, but those pixels would be arranged in a triangle, not a circle. That single, grainy image would change everything. Beyond observation, there is the dream of visitation. Concepts for interstellar probes like the Breakthrough Starshot Initiative envision sending tiny, laser-propelled sails to a nearby star system within a human lifetime. While such a probe would be a speck speeding past its target, its onboard cameras could capture images from within another solar system. If a tetrahedral world existed in that system, we would not just see its shadow against its star. We would see it hanging in the black, a geometric jewel catching the light, its true form undeniable from up close. These are not fantasies. They are blueprints and funded projects representing the exponential curve of our curiosity. For centuries, we knew only the planets of our own sun. Then, in a few decades, we found thousands of others, but only as statistical ghosts. The next leap is to see them as actual places. The tools to settle this debate are already on the drawing boards, being polished in clean rooms and waiting for their launch dates. The message is one of profound patience and optimism. We have not found a tetrahedral planet yet, perhaps because we have only just learned how to look. Our instruments are evolving from listeners to observers, and soon they will become cartographers of the alien. The silence of our current data is not a verdict. It is an invitation to build a better lens, to train a sharper eye on the dark, and to finally ask the universe for a clearer picture. The answer may be waiting, not for us to guess, but for us to see. The search for cosmic pyramids is not a spectator sport. It is a shared human endeavor, and you hold a vital tool for discovery right now, your own curiosity. Every time you look up at the night sky and wonder what else is out there, you are participating in the same fundamental quest that drives astronomers. That sense of wonder is the engine of science. To keep that engine running, you can follow the work of missions like the James Webb Space Telescope or the upcoming Nancy Grace Roman Space Telescope, whose data will be public treasure troves for anyone to explore. Organizations like the SETI Institute and the Planetary Society are not just for scientists. They are communities for anyone fascinated by the possibility of life and intelligence beyond Earth. You can support their research, follow their blogs, and become part of a global network of people watching the cosmic horizon. For a more hands-on role, the digital universe is waiting for your eyes. Projects like Zooniverse host real scientific research where volunteers help classify galaxies, spot new planets, and analyze stellar data. While SETI at home may have concluded its classic distributed computing project, its spirit lives on in other citizen science initiatives that use your computer's idle time to sift through radio signals or process astronomical images. You are not just watching the search, you can be part of the algorithm that finds the anomaly. And this conversation does not end with data. The most exciting ideas often begin as science fiction. What do you think a tetrahedral world would be like? What purpose could its builders have had? Share your own theories and concepts in the comments below. Your imaginative spark might be the very thought that inspires a new line of inquiry, a fresh way of looking at the data. Together, we are more than an audience. We are a community of mystery solvers, each of us adding a piece to the grand, unfinished puzzle of the cosmos. From the crushing embrace of gravity to the silent mathematics of a crystal lattice, from the chaos of tidal forces to the patient logic of a von Neumann swarm, we have walked the razor's edge between the possible and the impossible. We have seen how the universe, in its most extreme laboratories, might forge a fleeting geometric shape, and how a mind of cosmic ambition might build one to last for eons. This leaves us with the enduring question, whispered by every strange day to point and every shadow that does not fit natural phenomenon or alien engineering. The answer remains hidden, a secret kept by the dark, yet perhaps the search itself is the true discovery. This quest for a cosmic pyramid is not merely about finding an object. It is about finding our own capacity to wonder. It pushes our science to its limits, forcing us to write new equations and build sharper eyes. It stretches our imagination, asking us to conceive of purposes and powers beyond our own. In the tension between these two explanations, between the laws of physics and the dreams of builders, we find the most human of all endeavors, the relentless drive to explore the unknown. We look up and ask not just what is there, but what could be. Whether the first tetrahedron we find is a freak of nature or a monument to gods, its discovery will be a testament to our stubborn curiosity, to our refusal to accept that the universe must only be as we have seen it so far. So keep wondering, keep looking up. The next great mystery might be written in the geometry of a distant star's dimming light, waiting for someone, perhaps you, to notice the pattern. If this journey through cosmic possibilities has reshaped how you see the night sky, consider sharing that wonder. Your engagement fuels this channel and helps us all look deeper. Subscribe for more voyages to the edge of understanding, and the next time you stand under a starry sky, remember, you are not just looking at points of light. You are looking at a million questions, and among them, just maybe, the silhouette of an answer.